in this problem we have to determine the expectation value of moment. So let us read the question. Consider the two lowest normalized eigenfunction psi0x and psi1x of a one-dimensional system. Then psi0x is equals to psi conjugate x and psi1x is equals to alpha del psi0 by del x, where alpha is real constant. This expectation value of momentum operator in the state psi1 is. So solution, we have psi0x is equals to psi0 conjugate x and psi1x is equals to alpha d psi0 into dx. Okay. Now, so expectation value of momentum is psi1 h minus I h cross del by del x to psi1 is equals to I h cross psi1 to del psi1 by del x. Now, is equals to 0 as both these states are orthogonal to each other. Consider the operator A on a smooth function x. The commutator value of here it is A. So we have to determine commutator of A cos x. Now A cos x is operating on psi of x. That gives us A cos x minus cos x into A of psi, which is equals to x plus del by del x of cos x into psi x minus cos x into x plus del by del x of psi x is equals to x cos x psi x plus del by del x of cos x into psi x minus cos x psi x plus del by del x of psi x. What do we get? First term would cancel here, so we would be having minus sin x psi x plus cos x del psi by del x minus cos x del psi by del x. That means minus sin x psi x. Thus the value of A cos x is equals to minus sin x. So our option A is correct. This problem is related at the one-dimension harmonic oscillator. Here, A and A dagger be the levering and raising operator of simple harmonic oscillator in units where the mass, angular frequency, h have been set to unit. If G0 is the ground state of the oscillator and lambda is a complex number, the expectation value of psi x psi in a state psi exponentially lambda A dagger minus lambda conjugate A cat 0. So we have A can be defined as A dagger minus lambda conjugate A. So the expectation value of x psi x psi. So average x can be written as psi x psi equals to 0 e to the power A conjugate star, or we can write it e to the power minus A. Okay, and we can write it here B e to the power A 0. Now this term can be represented as further 0 x 0 plus 0 commutator of Ax 0. Here we have used identity. A to the power A B is to the power minus A is equals to operator B plus commutator of A with B plus 1 by 2 A B plus so on so. So here plus vanishing term. So we are left with first two term only. The contribution 0 x 0, the value of inner product of this is 0, so we have to evaluate this term. Now Ax is defined as h cross by twice m omega into lambda star A minus lambda A dagger into A dagger plus A, which give us h cross by twice m omega lambda star A square plus lambda A dagger minus lambda A dagger square minus lambda A dagger A. Similarly, XA would be h square by twice m omega A dagger A plus A to lambda dagger minus lambda star A, we would get root over h cross by twice m omega to lambda A dagger A square plus lambda A dagger minus lambda conjugate A dagger A minus lambda conjugate A square. So commutator of AX is equals to root over h cross by twice m omega lambda conjugate A star plus lambda A dagger minus lambda A dagger square lambda A dagger A minus lambda A dagger square plus lambda A dagger minus lambda conjugate A dagger A minus lambda conjugate A dagger square. So A commutator of X will turn out to be root over h cross by twice m omega lambda conjugate plus lambda into A dagger. So average X is equals to psi X psi is equals to h cross by twice m omega lambda conjugate plus lambda into 0 A dagger 0 is equals to 1 by root 2 lambda plus lambda conjugate. Here we have used h cross m omega equals to 1. Thus our option is T. This problem is related to Pauli's spin matrix, and according to this problem, the 2 by 2 identity matrix and Pauli's matrix is sigma x y sigma do not form a group under matrix multiplication. The minimum number of 2 cross 2 matrix which includes these 4 matrices and form a group under multiplication is. So in general, all these form matrix I, sigma x, sigma y and sigma z do not form a group under matrix multiplication. Okay. Now further consider 4 2 cross 2 matrices that include I, sigma x, sigma y and sigma z. These matrices satisfy the following relation. That is sigma x sigma y equals to I sigma z, sigma y sigma x equals to minus I sigma z, sigma x sigma z equals to I sigma y, sigma z sigma x equals to, that is minus I sigma y, third sigma y sigma z is equals to sigma x sigma z sigma y is equals to minus I sigma x, and fourth I sigma z square is equals to I. Thus 16 matrices are required to form a group under multiplication. I sigma x sigma y sigma z minus I sigma x sigma y sigma z, I capital I sigma x I sigma y I sigma z minus I sigma x minus I sigma y I sigma z. So our answer is 16, option D. This question is related to relativistic electrode or relativistic quantum mechanics, in which the dynamics of free relativistic particle of mass m is governed by Dirac-Hamiltonian, where the p is the momentum operator and alpha beta are 4x4 Dirac matrix. The oscillator operator can be expressed as, so here H is defined as C alpha dot P plus beta MC square. Further, rate of, we also know that the oscillation of free particle is given by A is equals to I by H cross H Hamiltonian V. So we have to determine commutator This problem is related to the time-dependent perturbation theory. A particle of charge q in one dimension is in a simple harmonic potential with angular frequency omega. It is subjected to a time-dependent electric field ETA e to the power minus t by tau square, where a and tau are positive constant and omega t is greater than 1. If it is in a distance past t tends to minus infinity, the particle was in its ground state. The probability that it will be in first excited state as t tends to positive infinity is proportional to. These are the options. So, we have Et equals to a e to the power minus t by tau square implies Vt is equals to minus Et dx, which is equals to minus qa x e to the power minus t by tau square. So, that is my potential. The transition probability from ground to excited state is given by first excited state is given by P is equals to 1 by h cross square integration 0 to infinity 1 Vt 0 e to the power I omega 10 t dt square equals to q square e square by h cross square mod inner product of 1x 0 square, and then here we would be having 0 to infinity e to the power I omega 10 t minus t. I would be writing it here into 0 to infinity e to the power I omega 10 t minus t square by tau square dt square. So, expressing the position vector in terms of dagger operator x cap equals to h. Further, a n cap is equals to n minus 1 root n plus 1 into n plus 1, and a dagger equals to 1. So, the value of inner product one x 0 is equals to h cross twice m omega 1 A dagger plus A 0, that means H cross by twice M omega and 1, or simply say now the time integral is given by 0 to infinity e की power I omega 1 0 t square by tau square dt equals to minus I pi tau 0 square e की power minus tau 0 square omega square by 4, where we have used the following identity to evaluate integral. 0 to infinity e की power alpha t square plus beta t, I omega t equals to minus I pi by alpha minus omega square by 4 alpha. So substituting values in probability transition, we get P is equals to 1 by H cross square Q square A square root over H cross by twice M omega square mod minus I pi tau 0 square per minus tau 0 square omega square by 4 का square, which is equals to Q square A square by H cross twice M omega pi T0 square e की power minus T0 square omega square by 2. This problem can be solved by using this identity only. I have discussed the complete solution for this problem. So our time dependence term would be minus half e to the power minus half omega t square, that is option A. This problem is related to quantum scattering. A particle is scattered by a center potential VR is equals to V naught R e की power minus mu R. So we have where mu naught, V naught and mu are positive constant. If momentum transfer Q is such that Q is greater than mu, the scattering cross section in Born approximation as Q tends to infinity depends. So we have to determine f of theta when Q tends to infinity. So scattering amplitudes, instead of Q, that is mu. Okay, stick its right Q. Amplitude of particle is given by f of theta equals to minus 2 mu h square q 0 to infinity r vr sin qr dr equals to minus 2 mu v0 h square q 0 to infinity r square e की power minus mu r sin qr dr. So the value of this integral would be minus 2 mu v0 by h square 3 mu square minus q square into mu square plus q square cube. Now I would be taking this can be modified further, mu v0 by h square. Now q square can be taken 3 mu square by q square minus 1 divided by q to the power 6 mu square by q square plus 1 cube. So f of theta in limit q tends to infinity, our reduced is to mu v0 by h square 1 by q to the power 4 3 mu q square minus 1 divided by mu square q square plus 1 cube equals to 2 mu v0 by h square 1 by q to the power 4. So where we have used 0 to infinity r square e to the power minus mu r sin qr dr equals to q 3 mu square minus q square divided by mu square plus q square का cube. So the scattering cross section is proportional to sigma theta equals to mod of f of theta is proportional to 1 by q to the power 8. This problem is related to quantum scattering. A particle in one dimension is in potential Vx a delta x minus a. Its wave function psi x is continuous everywhere. The discontinuity del psi by del s at x equals to a is. So we have to check up its discontinuity. Now the Schrödinger equation for such a particle is h psi equals to e psi, where h equals to minus h square by twice m del square by del x square plus v of x, where v of x is equals to a delta x minus x0. Here and E is the eigenvalue corresponding to eigenfunction Hamiltonian operator. So minus h square by twice m del square psi by del x square plus a delta x minus x0 psi of x into e psi of x, which modifies it del square psi by del x square plus twice me by h cross square psi equals to twice ma by h cross square delta x minus x0 into psi. As the potential is attractive when E is less than 0, the equation takes the form del square psi by del x square minus alpha square psi equals to twice ma by h cross square delta x minus x0 psi with alpha square is equals to twice m mod e by h cross square. So this solution everywhere except x equals to x naught must satisfy the equation del square psi by del x square minus alpha square psi equals to 0. The solution of equation R is given by psi plus x equals to a alpha x plus b a to the power minus alpha x greater than 0 psi minus x equals to c e to the power minus alpha x when x is less than 0. So the wave function must vanish at x is equals to 0, that is psi positive x is equals to 0 is 0 implies a plus b equals to 0 implies a equals to minus b. Using boundary condition, psi minus x0 we have a to the power alpha x0 minus a to the power minus alpha x0 equals to c minus alpha x0. Integrating the equation. Which one? This one. Rewriting the equation 1 from minus lambda to positive lambda, being an arbitrarily small number, a small positive number, we get del psi by del x minus lambda to positive lambda minus alpha squared integral minus lambda to positive lambda psi dx equals to twice ma by h cross square minus lambda to positive lambda x0 psi of x dx. As lambda tends to 0, the above equation takes the form that is psi by del x at x is equals to x naught plus minus del psi by del x is equals to x naught minus equals to twice m a by h cross square psi x0. Thus, our correct answer would be, here x0 means A. So our correct answer would be option A.